In this episode, we're going to have a look at common thermal distortion, climbing from thermal into wave, and a reminder, some bits of the wind tunnel app. Considered safe solo? Got the glider, but are you struggling to break the glass walls and fly cross country? Gliding in lift and G-Sync can help. Thermal distortion. Humids maintain size and stability. There is minimal entrainment or no conduction, so the humids maintain size and stability. It will accelerate entering drier and or cooler air layers. Entrainment. Consider an ice cube rising to the surface of water. A small amount is lost, but only on the surface. Or a tennis ball flying through the air that is on fire. Whilst the tennis ball is losing heat to the surrounding air, the air is gaining heat. The central core remains hot. If a thermal expands by entrainment, it must lose buoyancy. Pure thermal hot air narrowing. Entrainment and conduction weakens the temperature difference between the thermal and the air block, but then enhances the narrowing and strengthening of the air within. Consider the airflow aerodynamics around a tennis ball. If the thermal is confusing, don't wonder. You might be in the bow wave. There's a little boundary layer on the edge there between the descending air and the rising air. And there'll be a little separation point as well, with a bit of choppy turbulence at this point. However, the center core of the vortex will remain intact. Thermal mass will increase. Relative to temperature, humidity will decrease and therefore weaken the thermal. But generally this effect is minimal. Of course, on very small thermals, the sort of things that come off bonfires, then these vortices will actually suffer so much entrainment they'll break up. We see air mass increase caused by entrainment over bonfires and chimney stacks. Thermal into wave. The following 17-minute video shows the transition from a thermal into wave. And this is flying an LS6. accelerating to leave. Not as the case may be. Riding a little bit of shear wave here. Still going up on the right. Higher. see if we can find it again. It's gone. Interesting. Can a thermal grow? It is important to remember that the edge only goes down relative to the vortex and is zero relative to the real world sink flow. A small amount of air can be drawn in from behind or from underneath due to a low pressure within the vortex. But whilst the thermal will grow, it will weaken as the overall temperature will be reduced. The exception to the rules then. Accelerated thermals have little boundary and abrupt shear. Very abrupt change of strong lift and sink, and there'll be no airspeed indicator gust in this indication. Variopeak and sudden variopeaking means you're not centered. So here you are flying, not centrally cored on the thermal, but off center. And this is where you need to be. Thermal distortion distribution is over the same width of 200 meters, so there's no benefit of a distorted thermal being wider. And note also there's no increase in the volume of air. So in this diagram we can see the 200 meters width of the thermal and the glider turn radius there at about 100 meters, a bit over 100 meters. And what we're going to do is introduce a distortion to this thermal. What we're having is a massive amount of cold air, dry air, descending from evaporated cloud at height on the left there. And what that does is whip up this part of the vortex very briefly. Before it has time to be transmitted through the rest of the vortex, though, it generates a surge updraft here. Whilst we're going around then, we get an indication that the center core has moved quite abruptly to a position over here. A plot through the thermal in terms of strengths gives an unequal level of lift indicated. We may well then think we need to recenter over here. And of course, perhaps you can see our best efforts to do this can end up with a bit of a disaster because we end up in the considerable sink on the other side. So here is considerable sink on the left, triggering a distortion on the vortex. We move our thermal across, move our glider across to try and center the thermal and hit significant sink. Looking from above then, it may have some temporary horizontal distortion, i.e. non-centered core. This is where we were, and we can see where we've moved to, and actually we don't get again. Briefly brushing the core on the correct side will give a higher average rate of climb. I'll give you a chance to climb into the core, which will rebalance itself a little higher up. Flat dome cloud bases then. Here's our very simplistic diagram of a cell. And here we have a slightly distorted cell. It means that the center must be a little bit warmer, so maybe a little bit faster at that point. Wind shear on thermals. Some texts suggest that rising bubble can continue its trajectory because the thermal bubble has momentum, but it does not. Whilst the thermal has mass and some rigidity, that's gyrorigidity, it does not have the physical solidity properties of a solid. So whenever there is an inversion, there will be a wind shear. The toroidal vortex can be destroyed very easily. The inversion immediately weakens any temperature buoyancy, which is the driving force of the thermal. After the initial trigger, varying degrees of instability with height is the controlling aspect which determines the varying strength of any thermal. If the bubble did act like the wind blowing on a mountain, we would be able to saw the upwind side of all clouds, and we would routinely see the cloud edges manipulated by the surrounding airflows. During power flying, I have never experienced or seen this. Note here the initial expansion is simply to the very hot air mixing with the surrounding air until the vortex stability has become established. So in other words, the hot air loses its heat through conduction and entrainment, but the humidity is not lost. We can see on the sides here the evaporating cloud as well, drawing the air on this side of that stream of man-made cumulus cloud, and it's also being repeated on the other side. So we're getting these two inward flows being generated by the evaporated cooling cloud on the edges of the cloud that's formed. And in this way, this mechanism in fact generates street, and you can see the castellations starting. So after the initial expansion, there is a physical limit as to how big a thermal can actually be, in just the same way as a raindrop is limited to how big it will be. So we can see this process going on in the next video link. Here we can see some orographic cloud. The wind is blowing the air, forcing it upwards, and as it rises it cools. I do wonder though if this also gives an indication of where the strongest hill lift would be in this particular ridge. Next thing we want to have a look at is the inversion effect then. So again, we can go to the wind tunnel app, which is a free version, and have a look at it, and we can see the effect of the inversion on thermals, how feathered streeting occurs, the rapidity of spread out. We can understand how fast that forms, the importance of haze caps in terms of finding strong thermals we can connect to. We also see the effects of hills and depressions, multi-vortexes climbing together without impeding each other, and accelerations. We can see trigger restrictions and trigger focal points for vortices. There is a tool available for smartphones and iPads at the kind of price that glider pilots like, i.e. free, which will help you appreciate the motions within fluids, or as far as we're concerned, the motions of thermals within the atmosphere. And it's called Wind Tunnel. It has other programs at the beginning with aerofoils and shapes and so on, which are all very good. But the one we're interested in is the Torus program. And when you get to it, you get a display like this. The first thing we're going to have a look at is if we make any motion through the air and make it move, it forms a vortex that you've seen with the vortex toy. So here we go from bottom to top, and you can see the vortex climbing quite nicely. And we climb in the vortices up the middle, up to cloud base or the inversion. If we have a look at a column of
air that's moving quite quickly, then you'll find that it rather resembles the cartoon diagrams of the exhaust of little cars or motorbikes, or the cartoon characters racing along the road. And you can see a series of vortices there which are quite happy, and the motions are sympathetic to each other. So in other words, they don't destroy each other. In this next one, we're going to have a look at the pressure differences within the vortex. And we see the blue shows an increase in pressure, and so there's a little increase in pressure towards the top and sides of the vortex. More importantly, we're interested in the different speeds within the vortex. So in this one, the colours will show the fastest movement within the vortex. And we can see it's up through the middle and out through the top. And even as it slows down, there's still a faster speed in the middle and out through the top, where we get our indicated gusts on the airspeed indicator. Firstly, let's have a look at the basic flow of the vortex. And as you can see, the motion of the vortex is just as per the smoke ring. As we approach the thermal, we'll experience the sink, then the lift, then the sink, with the outwards flow of the vortex. In this one, what I've done is drawn effectively an inversion at the top. And the question is, what happens when our thermals get to an inversion? The vortex is fine until it gets to the inversion, and then it spreads out. On a day with an inversion where sometimes a little bit of wispy cumulus occurs at the inversion, we often say look for the haze caps and go for them. And so now we're going to have a look at what happens. Those thermals have got a little bit of humidity in them, so they punch a little bit higher than the general inversion. And we're going to have a look at what happens to the vortex when it hits that haze cap. The other aspect is, being a blue day, or essentially a blue day, then it will be streamed up by thermals coming up behind it. And so now we're going to see what happens in that situation. So here's the first thermal going up, and then there's one behind it, and one behind it, and one behind it. And in this particular case, quite unusually, the vortex is getting bigger and bigger and bigger, and deeper as well. And that allows us to connect with stronger thermals and go much higher, much more quickly. In this example, the grey line at the bottom represents the ground. And we're going to have a look at a supposed vortex being triggered from the ground. And we can see the vortex doesn't actually start at ground level. It starts actually about the height of the depth of the vortex itself. So kicking off here, and to the right, here, and then the vortex will carry on going. The thing is that over flat ground, there's nothing to restrict the airflow going in to replace the air that's lifting up. In this drawing, again, the grey line represents the ground. And what we put in here is a quarry or a dip or even a break in trees. And some people advocate that basically look down, and if you feel that it's a place where you would find it's warm, this makes a good hotspot. Well, in reality, if it's in open ground, that's true. But when it's like this, a quarry or a clearing in the woods, when we try and make a vortex coming out of this supposed hotspot, let's see what happens. Nothing. It can't actually escape because the air around it can't get in. In this diagram then, the grey line represents the ground again, and on this one we've got a peak. What we're going to do is compare a thermal from the flat ground to the thermal from the peak. You can see that the vortex forms very quickly after the top of the peak. To the right, it's higher before the vortex forms. Again to the peak, up it goes. So peaks, the tops of hills, especially if there are no trees on them, for example, are excellent triggers, hotspots for thermals being generated. To the left, the grey line represents a hill, and maybe it's south-facing, and so it's getting nice and warm, and so hot air is being produced by conduction. If the wind is blowing along it as well, then we would perhaps appreciate that there should be a thermal being triggered off. But actually, as we stroke warm air parallel and next to this hill, we find a vortex doesn't get triggered off in the normal way. You can see the left half of the cell in this example is completely broken away. And the vortex is destroyed, just as we see in the smoke ring against the screen. In this example, this is a series of buildings or houses, and I'm going to stroke just above them to see what happens to the vortex. And we can see essentially a mess. There's no clear defined thermal coming off because all of those buildings are preventing a smooth flow for the generation and trigger of the vortex. This time what we're going to do, I'm going to present a series of vortices all over the screen. Bear in mind that as it falls off the top it reappears at the bottom, and if they go off the right they reappear on the left, so it's not quite a perfect picture. But you'll see that the motions are sympathetic to each other, which is why we can fly in weak thermals next to stronger thermals and so on. And as they reappear at the bottom, the vortices are still occurring. What's important to remember is that this is just motion of fluid, of air, with no buoyancy whatsoever. The reality is the vortices that we experience gliding are considerably more stable because the buoyancy through temperature or humidity continues to be the driving force.
So in summary, we've had a look at the common thermal distortion, which includes climbing thermal into wave, and some aspects which are useful to understanding how fluid dynamics works on the wind tunnel